Hello, we're Group L6 of the Mechanical Engineering Department at Rutgers University. My name is Elliot Kang, the group lead for this project, here with Kalman Carmel, Okal Ombwayo, and Maxwell Winters.
Our senior design project focuses on building a 3D printer capable of printing elastomeric composites. Elastomeric composites are a type of elastomer that have been enhanced by adding nanoparticles such as graphene. The resulting liquid mixture has updated chemical properties. For example, it could be a stiffer and tougher material. Constrained with a budget of $650, we chose to use the method of fused deposition modeling as it is very cost efficient. Since FDM printing is not optimized for printing liquid material, some modifications must be made to print in the liquid phase. While this printer must be capable of printing a variety of elastomers with ranging viscosities, we will be testing our design using EcoFlex 0050, a silicone elastomer.
For the conceptual design, we chose a Creality Ender-5 printer as our standard base model. The reason for this decision being, the printer offered room for modification to enable us add systems like a peristaltic pump and a reservoir. This modification facilitated the printability requirement for an elastomer composite, which from the problem statement was our main objective, to print an elastomeric composite. With modifications comes challenges. These challenges, to list but a few, we have clogging due to nanoparticles. In this instance, more likely at the nozzle. Other problems that may occur include the elastomer curing in the system before it's printed out, and finally the problem of non-uniform particle distribution, as we added graphene nanoparticles to the elastomer. Therefore, we expect non-uniform distribution within the composite. The initial concept, we had a string-like mechanism that was supposed to push the elastomer composite as we printed out the materials, but due to the high viscosity nature of the elastomer composite, Dr. Balassi suggested during our first feasibility meeting that we would run into challenges with this design. Therefore, the final design of our printer was based on these ideas, modification like the pump system that will help move the elastomer composite. Other solutions that were added during the design process include building out the highly damaged dysfunctional parts with systems that are cheap and easy to replace.
The printer that we decided to modify for our project is the Creality Ender-5 3D printer. Modifying an already existing 3D printer allows us to focus on designing and manufacturing components specifically related to elastomers and avoid spending time on components like the frame, printing bed, and 3-axis motor system. This printer was an ideal fit for our project because of its accurate and efficient printing at a low price point, as well as prior experience that members of our team had working with this printer. In addition, the printer's modular design and pre-existing CAD model will make it much easier to design and integrate the modifications that we will be making to it.
We settled on a peristaltic pump design powered by a high torque stepper motor for our printer because it is more suitable for pumping highly viscous fluids. The inclusion of a stepper motor, controlled by an Arduino board, allows us to adjust the rate at which the liquid is extruded, assisting in controlling the curing process. This pump housing and roller system is made from an easy-to-machine aluminum block, slippery carbon-filled peak rollers, and compression springs, which provide enough force to create a vacuum seal within the tubing, resulting not only in applying positive pressure to the extruder nozzle, but negative pressure drawing material from the agitation reservoir.
The agitation reservoir will be where the mixed EcoFlex will be inserted into the 3D printer. The rotating mixer prevents premature curing and nanoparticle buildup while the material is being stored prior to printing. It will also ensure that the nanoparticles are evenly dispersed throughout the EcoFlex. The inside of the chamber will be chemically resistant to the EcoFlex, which will allow for much easier cleaning of the chamber in between uses. When printing begins, the EcoFlex will flow into a funnel at the bottom of the chamber and into the feeding tube.
With the design season for the project now at a close, we are slightly behind schedule and we intend on finishing up the remaining work over winter break. The only incomplete parts are to make some minor improvements to the CAD drawings and install it virtually on the Ender-5 assembly file. During the manufacturing season, we plan on building an actual prototype for testing purposes. And while we don't have any numerical analyses at the moment, the upcoming qualitative tests serve to ensure each subsystem will be able to complete its intended function or indicate where adjustments are needed. The following two images are the Gantt charts for each semester. Each task is listed and separated into categories with a designated student responsible for a particular task. However, for the spring Gantt chart, all of the tasks have not been started yet because they require the ordered materials. There will definitely be some challenges due to COVID, and we hope to continue with our project following the plan laid out in this chart for the upcoming semester. Thank you for listening to our presentation of our 3D printer capable of printing with elastomeric composites, and if you are interested in learning more, please feel free to contact us with questions or comments.